Okay, so related rates, this is day 2 of Unit 4. And related rates has, like, we'll spend 2 days on this. So I hope to get through 4 examples. If we only get through 3, so be it. But hope to get through 4. Related rates are applications of implicit differentiation. Often we are finding the rate of something with respect to time. So t is our independent variable, meaning we'll be taking derivatives with respect to t. Take a derivative with respect to t. And that will give you a rate because you'll have t in the bottom. So a couple of examples from yesterday. dV dt, that would be change in volume over change in time. Looking ahead, number 2 says find the rate at which the area of the circle is changing. So that would be dA dt. That would be change in area over change in time. So a whole lot of dt's in the bottom. That way we're looking for rates. How is something changing with time?
Do you ever use a triangle for change in?
Okay, that is a great question, because a triangle is algebra change.
That teacher last year always used that.
But that's not a calculus change. That's a V2 minus V1 over T2 minus T1. But if we let that delta T shrink to 0, then we've got an instantaneous change, and that turns it into a derivative. So they're related, but this is an algebra slope, this is a calculus slope.
No, I was just saying, like, for the term, like, just to write it out. So
Well, we write it out, but when we say the rate at which the area of the circle is changing, we don't mean algebra slope, we mean calculus slope.
Mm-hmm.
So
I just think that's
dA.
like a way to write it out, like change in.
Oh, just to put,
Yeah, just-
instead of, yes, that would be fine.
Yeah.
Yes. But we do have to be careful, because that triangle is the algebra change with 2 points, the algebra slope. The dV dt, dy dx, that's a instantaneous change, or an instantaneous slope, the calculus slope. Okay, example 1. Suppose y equals 5x squared minus 6x plus 2. Find dy dt when x equals 4, given that dx dt equals 2 when x equals 4. We've got a lot of words here, but the main thing is find dy dt. So I want dy dt to show up, so I'm going to take the derivative with respect to time of both sides of my equation. It feels like every year in math you learn something else you can do to both sides of an equation. Like in 7th grade you could add 3 to both sides, and later you thought, oh, we could divide both sides by 12. And then later, like in high school, you realized you could square both sides or square root both sides. And probably not till pre-cal did you take the log of both sides. Now we're going to take the derivative of both sides. So the left-hand side would just be dy dt. The right-hand side, get a little bit tricky here, maybe. What's the derivative of 5x squared? 10x is partially right. It's not wrong, it's just not finished yet, because we are taking a derivative not with respect to x, but with respect to t. So I need a dx dt. It's a chain rule thing. Like the very innermost thing, the derivative of x with respect to t is dx dt. Which is why I took the time to write d dt on both sides, not d dx on both sides. How about the derivative of negative 6x? Well, negative 6, but also dx dt. And the derivative of 2? 0. And it doesn't matter what derivative we're taking with 2. Like the derivative of a constant is 0. It doesn't matter the bottom variable. Great.
Can you explain when you would do the when you multiply it by the derivative? I feel like I would never know to do that.
That is, you've diagnosed the frequent problem correctly. Like people leave off the dx dt all the time. So I will address that in a minute. Emma, did you have a same question? Okay, you guys are on it. It matters what you're taking a derivative with respect to. That's kind of the big deal, right? If you're taking the derivative with respect to x of 5x squared, well, that's still 10x. But now, I guess if we want to really do the chain rule, we would do the derivative of x with respect to x. But now you see why we don't ever write that. I mean, it wouldn't be wrong, but dx dx, that's just 1, so I don't need to do that. So if the variables are mismatched, then you'll have this extra term. Does that kind of answer the question? Emma, does that kind of answer the question? So it very much matters what derivative.
Depends on what the denominator is.
It depends on what the denominator is. So we could even just make up a variable. Let's say dA of 5x squared.
Or you can do dx over dx with the regular.
So it's still 10x and then dx dA.
Okay.
Be careful with the primes. The prime means derivative, but if you use a prime, I don't know what your denominator is. Does that make sense? I don't know if that's dx dA or dx dt or dx d something else. So be careful with the primes because, silence it, put it away. Be careful with the primes because it's not clear what the denominator is. People will still use it because if every derivative in the problem is with respect to t, then we kind of just know that x prime means with respect to t. But that's kind of dangerous. So I won't ever do that. But if you do and you're careful, you can get away with it. Okay, the rest of the problem is easy because now we're just plugging pieces in. Find dy dt when x is 4. So 4 goes in for x. dx dt is 2. So 2 goes in for dx dt. 2 goes in for dx dt. Overkill it with colors here. That would be a safe stop. Let's see, 80 minus 12, and this is why you probably should use safe stops in case you mess up 80 or 12 or 80 minus 12. But there's your multiple choice answer. All right, but that was just x's and y's and t's. Let's get into real world stuff here. A pebble is dropped into a calm pond, causing ripples in the shape of concentric circles. Right? Everybody's seen this. You've tossed, guys especially, if you like, toss as big a rock as you can in the pond to make a splash, but then the circles emanate outwards. The radius of the outer ripple is increasing at a constant rate of 1 foot per second. Right, I'm just trying to visualize this. So that outermost circle, the radius is getting bigger at 1 foot per second. When the radius is 4 feet, find the rate at which the area of the circle is changing. So it's obviously getting bigger, and the R is expanding at 1 foot per second, but we want to figure out how big the area is changing. In fact, you know what? We should probably label that 1 foot per second. What do we know what that is in terms of variables or derivatives? The radius is increasing at a constant rate of 1 foot per second. So something is 1 foot per second. The derivative of, like, what's changing? Like, what in my problem, what in my picture, what in the real world is changing? The area and the radius, but that 1 foot per second is the radius changing. And what's the denominator? What's it changing with respect to? By the way, you can usually use units to figure some of this out. Like seconds is in the bottom. That sounds like a unit of time. So that's dr dt. And we're trying to find dA dt. How the area is changing.
Why would you not change the radius to like area? Because isn't pi r squared?
That's what's next. Yes, area is pi r squared. But I'm not just going to plug in, like I could plug in 4 for the radius and I'd get the area to be 16 pi, but that doesn't tell me how the area is changing. So if I want to find dA dt, I need to take a derivative of both sides with respect to t so that dA dt will show up. Right, like the reason I'm taking a derivative of both sides is to force dA dt to show up, because that's what I'm looking for. That's what I want to find. All right, Selah, what's the derivative with respect to t of pi r squared?
2 pi r and then dA dt.
Oh, so close. That's pretty good for the very first popsicle stick I pulled on this lesson. So 2 pi r, definitely that. And then I need to take the derivative of that innermost thing. You want to alter your answer? I think you said dA dt.
So is it dr dt?
It's dr dt. Again, for a first popsicle stick, that was good. Okay, do I know or have everything in here that I'm looking for? Like, I'm trying to find dA dt. Do I know r? Yeah, r is 4. And I know dr dt, so I'm ready to plug things in. dA dt, 2 pi. I'm going to do something that you guys rarely do, but you should do it, especially in physics you should do it, and that is plug in with your units. So r isn't just 4, r is 4 feet. And dr dt isn't just 1, it's 1 feet per second. This will also help confirm that your answer is right when you do the units. So 2 pi times 4, that'd be 8 pi. And what will my units be? Feet times feet per second. Feet squared per second. Does feet squared per second sound like a good unit for dA dt? Yeah, it's A is feet squared, time is in seconds. So I feel pretty good about this answer, at least unit-wise anyway, because that's feet squared per second. That sounds like an area over time. The other way to do this problem is to just know that if it asks for dA dt, like you're already going to know what the units should be. That's, I think, how most people do the problem. Like that way you can get the units right without even getting the problem right, because it has to be feet squared per second. And there are problems on my test and on the AP test where one of the questions will say include units. If it says include units, units is worth a point, which means even if you forget all of this stuff and you just say, well, I don't know, but the unit's got to be feet squared per second, then you're going to get some credit on that question. Questions on that one? Oh, I have a little note here. 8 times 3 is 24, but pi is a little more than 3, so just to try to get a sense of the problem. The area of that circle is expanding by 25 feet squared every second. I don't know. I don't have a good feel if that seems reasonable or not. On some of these problems, you get a feel for them, or if you get, 5 gazillion feet squared per second, hopefully you'd realize that seems a little bit big. So try to make sense of your answer when you get an answer at the end. Number 3. Water runs out of a conical tank at a rate of 2 cubic feet per minute. There's my conical tank. Yeah, it's fine. I think 4 might be easier than this one, but we'll do them both. Conical tank, 2 cubic feet per minute. What's 2 cubic feet per minute? Feet cubed per minute. Do we know what that is in terms of variables or derivatives? Here's where we could kind of go backwards. If you know the units, you can figure out the derivative. What is feet cubed a unit of volume? And what is minute a unit of time? So they just told me that dV dt is 2 feet cubed per minute. It's still not quite right. I don't know if anybody's catching this or not. This would be it. Water runs out of the tank. So my water level is dropping. What'd you say, Braden? Is negative. The amount of water in the tank is decreasing, so the change is negative. We're losing 2 feet cubed per minute. The radius at the top of the tank is 5 feet. Okay, so that's not necessarily like the radius of the water, unless the tank was full. The radius is 5 feet, and the height of the tank is 10 feet. Oh, I've kind of got lazy and dropped the labels, but everything in the problem is in feet, so I'm not worried about keeping up with the labels. That's dangerous, but if everything's in feet, I'll be okay. How fast is the water level decreasing when the water is 4 feet deep? So I'll say when h equals 4, find, what am I trying to find? How fast is the water level decreasing? The rate that what is decreasing? Okay. Use a variable. Which variable is decreasing? I already know the V is decreasing at 2 feet cubed per minute. Like that's the volume. It wants the level. So that would be like the height of the water. So it's asking us to find dH dt. Find dH dt. This time they were kind enough to give us the equation. And then this is why this problem is a pain. I know I want to take derivative with respect to time of both sides to make dV dt show up. What happens on the right-hand side if I take a derivative? What am I going to have to use? The product rule and the chain rule. And dH dt will show up. That's nice. But dr dt is also going to show up. And now I'm going to have a mess on my hands because I don't know anything about dr dt. So I need to figure out a way, like, if R and H are related, are R and H related? Because I would really like to make one of them go away. Like, is there an equation that ties together R and H? because then I could substitute that in there. I really would like my R's to go away because I want a problem with H in it. So does R equal anything over here? So it's 5 at the top, but R is changing, so we have to be careful. I don't want to just plug in 5 because that 5 is changing. Somebody said it. Barry, did you say that? But R is always H over 2. It's like a triangle thing going on in there. However much water is in there, R is half of H. R is half of H. This is the trickiest of these problems. So, I mean, you'll see one again, but this is the trickiest of the group. So I'm going to... Well, it's going to depend on this initial setup. So, like, if this had been 10 and 10, then you could just say R equals H. That'd be nice. But if it was like 3 and 12, then it would be 1/4 H. So you use those initial dimensions to figure out this R and H ratio. And I know that's a pain, but it's going to make life so much easier. Let's clean this up before we take a derivative. 1/3 pi H cubed over 4. I'll even go one more step. 1/12 pi H cubed. We did not want to deal with the product rule and have actually three derivatives, because we would have had dv dt, the r dt, the h dt. This would have been a nightmare. Once we figure out how R and H are related, now we only have one variable. So now it's much easier to take a derivative of both sides. Barrett?
H squared over 4, why would that not, wouldn't it be 4H over 4 times H squared over 4?
Let's see, 1/3 pi. I square the top and the bottom.
Because if you're putting it over 4,
And then I'm just multiplying across. Okay, left hand side dv dt. Right hand side, here we go, Will, help us out. What's the derivative with respect to t of 1/12 pi h cubed? Well, you're not wrong. You left out a few things, but you weren't wrong in what you said, so that's not bad. So yes, 3 pi h squared. Somebody help him out. What's the rest of this? dh dt. And then there was one other minor thing you left out, Will? Like the 12 over 12. So that would reduce, so pi h squared over 4 dh dt. Well, running out of room. Let's start over here. dv dt equals pi h squared over 4 dh dt. Okay, now let's start plugging things in. We know what dv dt is. That's -2. Pi over 4. H is, what are we using for H? I got all kinds of numbers in here. Oh, that's a tricky one, maybe. Like, this H is 10, but it says when the water is 4 feet deep. So I'm going to use 4 for H. 4 feet deep, that 4. And the HDT is what we're looking for. Okay, so -2 equals 16 over 4 is 4 pi h dt. I'm almost out of room, but I'm also done. Negative 2 over 4 pi is dh dt. I did not keep up with units, but I can get units from dh dt. So what are the units of h? Feet. And what are the units of t? Time, that's minutes. So that answer has to be in feet per minute. I got a negative. Does that make sense in the context of this problem? Why does that make sense? Right, yeah, we're losing water, so the height of the water is going down. So I'm a little nervous about the negative, but I think it makes sense in terms of the problem. All right, in my mind, that's as bad as it gets. We might have time to do example 4. It'll be tight. We can do it. Yeah. A 13-foot ladder is leaning against a wall. Suppose that the base of the ladder slides away from the wall, so that's down here. The base of the ladder slides away from the wall at a constant rate of 3 feet per second. That sounds like a derivative. It sounds like a d something dt, but I don't know any variables yet, so I'll just label it 3 feet per second. How fast is the top of the ladder sliding down the wall? So this is what we're looking for. It's like, how fast is that spot going down? Because it might not be exactly 3, even though those are like tied together. It's kind of weird. In fact, it's not 3. When the base of the ladder is 5 feet from the wall, indicate units of measure. Okay, we need to put some variables on here. This looks like an a squared plus b squared equals c squared situation. So let's use a and b. In fact, let's just go ahead and write a squared plus b squared equals c squared. They said when a is 5. I mean, they didn't say a, but they said 5 feet from the wall. Which means that this 3 feet per second is how a is changing. A is getting bigger. So that's my dA dt. Do we know what variable they're asking for up here? Like, that's what it is in the picture. That's dB dt. It's how b is changing. Well, let's take a derivative of this thing and see what we get. So 2a dA dt. All my variables are different, so I'm going to get lots of variables and lots of derivatives in this one. 2b dB dt equals 2c dc dt. That looks like great fun. One of those, though, makes this problem a little bit easier. Like A is changing, B is changing, but this ladder is not changing length. So do you know what dc dt is equal to? If the ladder is not changing length, that's 0. That's not changing. So that makes that part of the problem nice. The ladder is not changing. Another way to say that is c squared is constant, and the derivative of a constant is 0. Well, is that what going to be? It's exactly what you were going to say, isn't it? Let's see. So I guess we could, I'll leave the 2's in there. 2 times a is 5, the ADT is 3. Right, I'm just plugging in my pieces here. I don't know b. I mean, maybe I know b. Any geometry all-stars remember that special right triangle? That Pythagorean triple is the fancy word? 12. 5, 12, 13. So B is 12. And dB dt is what we're looking for.
Would you be negative 12 because it's going down?
Well, the length is 12. dB dt is going to end up being negative. In fact, I'm going to safe stop the heck out of this thing. Negative 2 times 5 times 3 over 2 times 12. How's that for a safe stop? So Barrett, why is this negative? You kind of just answered that question. The ladder's moving down, so B is getting shorter. So it makes sense that that is negative. Okay. Let's make the assignment just 1 through 5. So try those 5 problems on the next worksheet. Monday is more of the same. We'll do 2 more examples. We'll work some of this worksheet. Tuesday we'll review, and Thursday we'll test. So if you were an all-star at this, you could test now. That's not very many of us. That's fine. We still got a few more days to learn this without adding extra stuff to it.
Yep.